Okay, let's get started. So I'm going to be talking about probability and statistics today, as the slides say. Just to judge, how many of you have seen probability plenty of times before or are pretty comfortable with everything? Has anyone never really worked with probabilities before other than in this class? Okay. All right, so I'm going to do it in a slightly different approach than Jeff did in class, which I'm going to do it in a way that maybe you've seen before, maybe you haven't. Kind of measure theoretic a little bit, but not any of the actual details. So to start with, when we're talking about probabilities, we have to talk about them relative to something. And what we talk about them relative to, we call the sample space. So the idea is we're doing some kind of experiment where experiment could be a lot of different kinds of things. And we have a set of all possible ways that that could turn out. So for example, if we're flipping a coin, we're going to say heads or tails. Of course, if you're flipping a coin in the real world, you might get it landing on the edge, rolling off the table. We're going to abstract away from that and only have these simple two possible results. We could also do, I'm going to flip a coin 3 times and look at the sequence of heads or tails that come out. And in that case, there's these 8 possibilities. We can also do something like an experiment could be ask a person their age. And in this case, the ages could, well, I guess it could be 0. Could be obviously anywhere from 1 to 100 something. Probably, we're never going to get someone saying their age. We're never going to get someone truthfully saying that their age is 500. But it's kind of hard to say what the actual maximum value of an age should be. So far in the world, it's 120 something, but there's no reason, like, we don't know for sure that no one's ever going to live to be 130. So to avoid choosing a maximum, we're going to just let it go out to any possible integer. And obviously that's a kind of not nice because we don't think anyone can ever live to be 10,000 years old, but we also don't want to choose a maximum. Choosing a maximum would be even worse. So we can just then assign very, very low probabilities to the very high ages. And since there's only been a finite number of people in the world, if we choose crazily low probabilities, it won't be inconsistent with how old anyone has ever lived to be in reality. Another thing we can measure is someone's height. So if we can measure their height exactly, then we get out a real number in inches, feet, whatever. So in this case, so we can see then that there's a couple different kinds of sample spaces we can get out. We can get finite sample spaces like these two. We can get discrete sample spaces like someone's age in years. Or we can get continuous sample spaces like someone's height. And so we have kind of finite, countable, uncountable are the main distinctions that we care about. Obviously, people who know, so there are sets of cardinality bigger than the reals, but we don't care about that distinction here. Okay, so now that we have a sample space, we want to define an event. And an event is something about the result of an experiment. So the way we're going to define it is just as a subset of the sample space. And that could be just heads. It could also be either heads or tails. So it could be any subset of omega, including omega itself. And then on these sets, we can do the normal union, intersection, complement, whatever we want to do with them. So it turns out that sometimes we don't want to allow any arbitrary subset, because especially when you're dealing with, say, the reals, you can make some crazy subsets that have really weird properties. So what we actually need for probability is called a sigma algebra, which the definition is it's a set that contains the empty set. If you take the complement of anything in it, it's still in it. And if you take a countable number of unions of anything in it, that's still in the sigma algebra also. It's also called the Borel field. But usually, if you're doing practical things and not doing math, you don't really care that much about this. You can just work with any subset you want. Okay, now that we've defined the sample space and events, we need to come up with a way to measure the probabilities. So there's different ways you can define probabilities. and you've probably heard of frequentist versus Bayesian arguments. We don't really care about that right now. We're just going to come up with a couple axioms, or we'll use the axioms that Kolmogorov came up with, so that a probability function is a function where it takes an event, so any heads or a person's age being between 30 and 35, and assigns it to it a real number, which is non-negative. And also, if you take the probability of the entire sample space, you get 1, because something has to happen. And this property called sigma additivity, which is if you have a bunch of mutually exclusive sets, so sets whose intersections are empty, and you take the probability of their union, you get the sum of the probabilities. As it's written here, so this could be probability of heads plus tails. So probability of heads union tails is equal to the probability of heads plus the probability of tails. As it's written here, you need to do it for any countable sequence of sets, but you can just take the first, say, 2 to be whatever sets you actually care about and put all the rest of them as the empty set. And then the empty set intersect anything is the empty set, so they're mutually exclusive. And their probability, as we'll see soon, is 0. So you can just stop this sum anywhere you want, and it's the same thing. Okay, so any of these arbitrary functions that satisfy these axioms will satisfy some other things that we can derive from the axioms. So we'll do a couple quickly here. If you have any event in your sample space, and you take the probability of its complement, what you get out is 1 minus the probability of that event. So how can we prove that from the axioms? Well, you can look at the probability of A union its complement. So first of all, by the definition of complement, A union its complement is the whole sample space. So that's the probability of just the whole sample space omega, that's 1. But you can also think of it as A is disjoint from A complement, because that's what the complement means. So you can look at it as the probability of A plus the probability of A complement is equal to this number. So 1 equals A plus A complement, and you just subtract P of A from both sides, you have that. Another thing that's always true of any arbitrary probability function is that the probabilities you get out need to be they can't be more than 1. So all probabilities have to be between 0 and 1. Does anyone want to tell me how to prove this using the 3 axioms we just had? Or the thing we just proved also. So we have 4 things to work with. Well, what we can do is we just take the whole sample space, plug it into this. So use omega for A. We have, oh, sorry, I completely just lied. That was the next one. So we can take the probability of A complement. That's going to be 1 minus the probability of A. And since we know that the probability of A complement has to be non-negative, 1 minus the probability of A has to be non-negative. So move the P of A over to that side, and you have P of A less than or equal to 1. Okay. The last thing we're going to show now is that the probability of the empty set is 0, which we actually already mentioned, and we kind of implicitly used here. So this is actually a little bit of a cyclic proof here. You can do it non-cyclically if you care about being philosophically sound. But the easy way, if you assume this is true, is that you just take the complement of the whole sample space, which is the empty space. 1 minus probability of the whole space is 1, you get 0. Okay, so that's basic definitions of probability functions. So looking at this example we had before of flipping a coin, getting heads or tails, we know from the axioms that necessarily the probability of the empty set is 0, the probability of the event of the whole sample space is 1. That's always true. Now, actually, this is called the trivial sigma algebra. We could just say, oh, this is the sigma algebra we care about, empty set or everything, and we could say that's done. But that's not very useful, because we can't actually talk about probabilities of anything we care about, and we can probably distinguish between the heads and the tails case. So we can assign the probability of heads to be p, any number between 0 and 1, inclusive. And then we're required that the probability of tails, because that's the complement of the event heads, has to be 1 minus p. And then that's all the possible events on this space. And so we've just defined what's referred to as the Bernoulli distribution, which most of you have probably seen before. Okay, moving on. You can derive a couple other useful things from the axioms about the various events. The probability of an event and the complement of another event is the probability of the first event minus. So this is easier thought about as a Venn diagram. So this circle can be A, this circle is B. So B and A complement is B intersect with the rest of the space that's not an A. So that's this part of B. So the probability of that thing is the probability of all of B minus this part. That's pretty obvious if you draw it, but you can prove it from the axioms. A few other things, you can do a similar thing with unions. The probability of A union B is this probability plus this probability minus this part because we counted it twice. And as a corollary to that, this is sometimes useful, that if you care about the probability of both A and B happening, but you don't know anything about their joint distribution, you just know the probability of A and the probability of B, then you can get a bound on them both happening because it has to be at least this probability, the probability of either of them happening summed minus 1, just in case, because you just get an upper bound on that has to be less than or equal to 1. Okay, and another identity, or not an identity, but if A is a sub-event of B, so if A happened, then B necessarily happened, then of course the probability of A can't be bigger than the probability of B. Okay, so far we've only been working with these arbitrary functions that are fine, but we kind of care about what they actually mean if we're going to use them. So one interpretation of probabilities is the long run. If you run the experiment over and over and over again to the limit, this is the portion of times that it would happen, that event would occur out of this experiment. So you can write that mathematically like this, add up ones and take the mean. Another way of interpreting it is the Bayesian approach, which is saying the probabilities represent my beliefs about whether this event will happen or not, which is kind of subtly different from this one where you're running things over and over again. Some things it's not possible to run over and over again. They're either true or they're not. So for example, we can talk about the probability that Joe is in Wien Hall right now. And Joe is either in Wien Hall right now or he's not. There is a true answer, but I don't know it. I don't know who Joe is. So I can talk about, oh, I'm like 30% certain that Joe is in Wien Hall right now. And you can assign that a number. And there's actually this thing called Cox's theorem, which says if you take these kind of common sense things that you would want such a way of assigning numbers to beliefs to work, various axioms that you want them to do, you end up with exactly the same probability axioms. So the two systems are mathematically equivalent. So we'll be using both kinds of approaches in that frequentist tools are nice when they apply, and that's great. And it's nice to have frequentist bounds on how good a thing will be. But we'll also be using Bayesian interpretations of reasoning about things that have a true answer, but we don't know what they are, and prior distributions and things like that. Okay, so by the way, if anyone, this is like a recitation, not a lecture, so feel very free to interrupt at any point if I'm ever being unclear, any questions, whatever. Okay, so we have these axioms and we know some things about the functions that satisfy these axioms, but every time we come up with a new probability distribution or a new probability function, we don't want to have to manually verify sigma additivity, because that's kind of annoying. So one thing you can do is say, okay, my sample space, I'm going to divide it into these atomic events, which we can call them omega 1, omega 2, whatever. There can be, if there are countably many of them, this necessarily works. If you have an uncountable sample space, you can't necessarily do this. But so you can have atomic events that are mutually exclusive. They can never happen at the same time. And you can have corresponding probabilities for each of them. And as long as those probabilities aren't negative and they all add up to 1, then you can have a valid probability function which just adds up all the probability values that correspond to the event you're talking about. So if you have an event that is like omega 1 union omega 2, then omega 1 and omega 2 are both in the, sorry, I'm being a little, by that I mean omega 1 union omega 2, which of course is just the set omega 1, omega 2. And so then this probability function is just add up P1 and P2. And that's kind of the natural thing you would do with a discrete distribution. Okay, so we have these probability functions, and we want to be able to do things with them. One thing we want to do is condition. So if we say we know that E2 is true, we want to know how likely is it that E1 is true, then we take this, so to start with P of E1, you can think just the area in this sample space. We have the sample space omega, we have E1. Then if we want to condition on E2, we draw E2, right? So what we're doing is we're shrinking our sample space from all of omega to just E2. And then the probability of E1 given E2 then is the part of E1 that lies in this sample space divided by the size of E2. So that's, in symbols, is just probability of E1 and E2 divided by P of E2. So that's kind of the definition of conditioning. And you can see, if you think about it as changing the sample space, you can immediately see why it's not well defined to condition on an empty, or an event of no size, because then your whole sample space has no size. And you can't talk about subsets of things that have no size. It doesn't really work. So that seems like a silly thing that Jeff mentioned in lecture and that I mentioned just now, but it actually causes problems when you're dealing with conditional or with continuous distributions. So if you're conditioning on a continuous value being equal to some value, you can do that in practice a lot of the times, but sometimes it'll cause problems because you're conditioning on an event of size 0 or measure 0, and that doesn't work. So you can also see, obviously, that if E1 and E2 don't intersect, then the probability of E1 given E2 is 0. Okay, so Bayes' rule. This is one of the most important things about probabilities in machine learning. And what we do, the way you derive it, Jeff did this in lecture, but I'll do it again, is you say the probability of A intersect B. I used a comma instead, it's the same thing. Is equal to the probability of A given B times the probability of B, which is just how we defined it just here. It's also equal to the other way, B given A, PA. So if you set these two things equal to each other, divide by P of B, you get Bayes' rule. P of A given B is P of B given A times P of A over P of B. So you can switch the order of the conditioning. And as Jeff mentioned in class, this is really important for machine learning in a couple of different situations. So the one he talked about was if you have a data set that you got from the real world, and you have a bunch of possible models that might explain it, and you want to say, which model is the best? How likely is this model to have generated this data? One way to do it is to say the probability of the model given the data is equal to the probability of the data given the model, which, if you have a generative model, that's what the model is. A model is a probability distribution over generating data. Multiply that by the probability of the model, which is something you have to define on what models you think are likely or not, and you divide by the probability of the data. So the probability of the data is annoying because it's not something that you can measure. I guess you could measure it if you got infinitely many different data sets and did density estimation on that. But in practice, that doesn't work. So, but the nice thing is if you're comparing models, this is constant across different models. And so it doesn't actually matter if you're just choosing the most likely model. Another situation is, say you're doing machine translation. You have some French text that you want to translate into English. So the probability of English given French, we can switch it. We can actually do the translation problem in reverse, which doesn't seem any easier, right? Why would it be easier to translate from English into French than from French into English? Well, the reason is that this problem is equally hard to estimate the French given English as it is to estimate English given French. But this adds the terms, the probability of the English sentence and the probability of the French sentence. So if we have a good model on what English sentences look like, then we can kind of weight how likely this English sentence was based on whether it's a good English sentence and kind of makes sense linguistically. And so switching the order of the translation actually is a nice trick to help kind of weight how good your translator output is. You add a term that's easier to estimate in there. So when you go to Google Translate and you plug it in, they don't actually do the reverse translation, but they do weight it in this way. So that's a nice trick. Okay, independence. This is an important concept. Two events are independent, which we can write that way, if the probability of both of them happening is equal to the product of the probabilities of either of them happening. You can equivalently talk about that in terms of conditionals. If the probability of A is the same thing as the probability of A if you know B also happened, so B doesn't give you any extra information about whether A happened, then they're independent. And if two events are independent, then if you complement either of them, it's still true. Okay, so conditional independence. That has basically the same definition where you just add a given C to all the terms. But one thing that can be confusing about conditional independence versus independence is you might think that if A and B are independent, then they're still independent if you add other information. And that's not true in general. Sometimes it's true. But so for example, if you have A and B are the Bernoulli distribution we talked about earlier, coin flips, either 0 or 1, and then Z is XOR. So if they're both 1, it's 0. If they're both 0, it's 0. If they're different, then it's 1. Then actually, A is independent of B because they're independent coin flips. A is independent of Z because if you flip A and you see Z, that doesn't tell you anything about which way B went. It's just that it doesn't tell you anything. Same thing with B given Z, because it could still be either one. But given two of them, the third one is absolutely known. So they're not independent anymore. So how do you actually define independence of more than one thing? So we just saw that pairwise independence isn't enough. Also, it turns out that just extending the same P of A and B and Z equals the product of the marginals is also not enough. You can come up with an example where it's not true. So the real definition is that it has to be true for any subset of the events. So that's pretty annoying to check in practice. Okay. So far we've defined probability functions on events within sample spaces, and we've talked about various things with those probability functions. But usually we don't care about events so much. We usually work with these things called random variables. So technically what a random variable is it's a function from the sample space to some other space. So one example of a random variable we've been talking about is whether a coin flip was heads. So you can set it to 1 if you flip the coin and got heads, 0 if you flip the coin and got tails. So that's a function from the set heads, tails to 0 or 1. If you do the same thing for the sequence and you just add up the number of heads you got overall, that's a function from these sequences of heads and tails to a number between 0 and however long the sequence is. So normally we talk about random variables that are either multidimensional, either scalars or multidimensional real numbers, or either multidimensional or single integers. But you can define a random variable that's anything. You can talk about a random, so this is random scalars, random vectors. You can talk about random matrices. Sometimes that's useful to do. You can talk about random graphs. You can talk about random anything. But in this class, we're mostly going to be worrying about random vectors. OK, so given a random vector, we want to talk about what its probabilities of taking on the various values are. So that defines the distribution of that random variable. So if you have a discrete random variable, one where the output, or sorry, I said domain. That's confusing. It's actually the output of the function. So it's a function from the sample space to something. And if that something is countable, then it's called a discrete random variable. And so one example of that we mentioned before was the number of heads when you flip a coin a bunch of times. And so that, if we want to talk about the probabilities of various events for that, there's kind of a natural definition of events, which is just one event for each value that it can take on. So for the coin flips, could be we have an event that the total was 0, an event that the total was 1, up to an event that the total was n. And so if we then just do what we did before and assign a probability to each of them, we get what we call a probability mass function. So that's a function from values of the random variable to the probability that the random variable takes on that value. So that's basically a table. You can just write it out as, for example, that's a graphical representation of a table. So this is for the coin flips. It's some very low probability that you get 0 heads if you flip a coin 10 times, a fair coin. Highest probability is 5 times. It's a table. So the property of these probability mass functions, PMFs, is that every entry has to be non-negative, and they have to add up to 1. But given those constraints, any function from a countable space to numbers between 0 and 1 that add up to 1 is a valid probability mass function for some random variable. OK. If you have more than one random variable and they're jointly distributed, so the values, the two affect each other, like for example, we had the XOR thing earlier, then you can think of the two different random variables as components of a single random vector. So if you have 2 coin flips, then you can think of it as components of some random vector that has 2 elements, where the first one is 0, 1, second one is 0, 1, whatever. And then the PMF on that is a multidimensional table. So then there's this important concept on that called the marginal, which we'll talk about a lot. So that's when you have jointly distributed variables, x and y, but you want to ignore y for now. So you only know about you either only know about or only care about the probability of x ignoring y. And the way you get that is you sum over all the possible values of y in the joint table. And the reason it's called a marginal is because if you have a table for x, table for y, they have probabilities in here. The marginal is the row sums. It's the margin of that table. So this element, x be 1, 2, 3, 1, 2, 3, 4. This is the probability that x equals 1, is the probability of x equals 1, y equals 1, et cetera. OK. Has everything so far been clear? Good? OK. So if you have random variables, you can also condition just like you could with events. So it's basically the same thing. So now the probability mass function of A given B is the probability of A and B divided by the probability of B again. But so when we're talking about this equality, we're talking about it as functions. So for example, probability, so P of A given B, as I wrote it here on random vectors, on random variables, is a table. And the way we get it from the joint table so if we have the same A, B, so to get the conditional distribution, what we do is we say if we're conditioning on B being this value, then the conditional distribution is just this part of the table, all of these elements for that particular value of B. And then we just have to rescale them so that it adds up to 1 and is a valid probability distribution. Is there a question? Okay. Sure. So the marginal distribution is if you have this joint P of X and Y, this can take on, so that's kind of a two-dimensional table of all the different possible pairs of values on X and Y. So we can, when we're taking an observation of X and Y, we run our experiment, we get out two numbers, X and Y. This could be the first coin, if we're flipping coins still, and we're flipping two coins now. X could be whether the first coin was heads, Y could be whether the second coin is heads. So in that case, they're independent, but they don't have to be independent. If you imagine drawing from a deck of cards, you can't draw the same card twice in a row. So it changes, so drawing X then slightly changes the distribution of Y. So this table then has the different probabilities for all the possible combinations of X and Y that you can draw. Sometimes you either only know about X, you only have observations of X and you don't have observations of Y. Or you want to know only about X and you don't care about Y. So in that case, you want just the probability of X, which is basically ignore Y, pretend Y wasn't a thing at all, and how would X be distributed? So you then take, the way you get that is you consider all the possible things that Y could be, add up or integrate over them, and then you get just a single number for each value of X. So in this table, it's every possible value of X. Or if X is 1, it could be X is 1 with Y is 1, 2, 3, or 4. So you add up all of those, and you get the marginal sums along here. And that's what you get. That's the overall distribution of X. Does that help? Okay, so conditioning is you take an individual row of the table or column, and you just take that bit. So here we have the joint table on A and B. We're conditioning on B being this value, call it 2. So we just rip out that table, that column from the table. Those are the possible things that A could be, given that we know B is 2. And then for it to be a probability distribution, we have to divide by the probability of B being 2. Same thing for independence. It's if P of A and B equals P of A. So if that's true for all possible values of A and B. So for independence, we have this is the condition for independence of two random variables. If this is true for all values of A and B, that the random variables can take on. So just to insert here, when we say IID, we mean independent and identically distributed. So that means we have a bunch of random variables that have the same distribution and they don't affect each other. So that's a very common assumption that we make in different statistical things so for example, if we're flipping a coin a bunch of times, the coins don't influence each other, presumably. So that's the bunch of coin flips would be IID. Something that wouldn't be IID or would be something like drawing from a deck of cards where you don't replace the cards, so sampling without replacement. Then the value that you got for the first one affects the later ones, and that's why card counting works. So in that case, they're not IID, but in that case, they are something called exchangeable, which means that if you take the sequence that you drew and you shuffle it up in any permutation, that's equally likely. Okay, so we have probability mass functions for discrete variables now. So now we're going to define the cumulative distribution function. So that's the probability of x being, of a random variable being less than or equal to some particular value. So that's useful all the time when you're doing semi-theoretical things. So for example, if you have a bunch of IID variables and you want the distribution of their maximum, that's easy to do with the CDFs. By what you do is you say the probability of the max being less than some value is equal to the probability of all of them being less than some value. Because if they're all less than a value, that's exactly the same thing as the max being less than a value. And these are independent, so you can just split that up. And then you just have the CDF raised to the nth power. Okay, so here's an example of what, this was the binomial, the number of heads in a sequence of 10 flips mass function. This is the cumulative distribution function, the CDF. So you can note that the negative infinity is always 0. Positive infinity is always 1, because it can't be less than negative infinity, so there's no probability of that. It has to be less than infinity, so that probability has to be 1. And in the middle, it's non-decreasing, and that's because it can only be more likely to be less than or equal to 2 than it is to be less than or equal to 1. Okay, if we have a continuous random variable, we can't do a mass function, because the probability of a continuous random variable being any particular real number is 0. And we know that's true, because if it weren't, so if you had, say, a normal distribution, and here's the most likely point, right? The single point, the mean. So let's call it 0. So but the probability that this standard normal is equal to 0, exactly 0, has to be 0. Because otherwise, since we have uncountably many points, so if we go like between there and there, if the probability there isn't 0, then the probability there also can't be 0, right? So the probability in there, for each real number in there, there has to be at least, let's call it A, probability mass assigned there. And so then we have A times the number of real numbers in there as the probability of being in this little interval. And that's infinite, because there are infinitely many real numbers. So the probability of taking on any particular value has to be 0. Does that make sense? Okay. But we can do a CDF in exactly the same way as for a discrete variable. So we just say the probability of being less than some value. And so for this standard normal, the CDF happens to look like that. So this has the same negative infinity still has to be 0, positive infinity still has to be 1, and in between it has to be non-decreasing. If it's actually a continuous random variable, then the CDF is continuous, because if you move epsilon along, you can only move a little bit up. So sometimes we define random variables that are actually mixed, and so in that case we have it's kind of a mixture of a discrete random variable and a continuous random variable. So you could imagine something like so Alex gave this example in class actually. If you take the distribution of incomes in this room. So for people who have any arbitrary job, that's going to be close to a continuous distribution. People usually have salaries in whole cent amounts, but we could pretend it's continuous. But then the probability of having the exact CMU grad student, whatever department salary is going to be more than 0. There's going to be a certain portion of the people who have exactly that salary. So that is an example of a mixed distribution. And in that case, the CDF is right continuous. So it looks like that, because the probability of being less than or equal to, the probability of being less than or equal to this number where it jumps is that you go slightly more, it's still continuous, but up to here, there's a discontinuity. So if there are jumps, they're always on the right. Okay, and we can do this for multidimensional things just by making a multidimensional function that is the probability of being less than or equal to in each component. Okay, so then for continuous variables, we still want something kind of similar to the mass function. So we have the density function, which is the derivative of the CDF. So that has the property that if you integrate it, for example, over negative infinity up to a value, you get the probability of the CDF. You get the CDF out. So because this is that derivative, it's non-negative because the CDF can never decrease, but it can be more than 1. It's not a probability, so there's no reason it's allowed to be more than 1. But it does have the property that it integrates to 1 because the integral over the whole space is equal to the CDF all the way out. The probability of anything happen has to be 1. So there's a PDF for a standard normal distribution. Okay, so a couple important distributions that I'm not going to describe in full detail now, but that will come up are the, so for discrete distributions, there's the Bernoulli, which we mentioned was the coin flip. There's the binomial, which is if you flip a coin a bunch of times, the number of heads you get out. And so these are both parameterized by the probability of getting heads. So this is an unfair coin flip. There's also the categorical distribution, which is a dice roll. So you have a bunch of different possible outcomes, and you assign probabilities to each of them. So it's like a Bernoulli, but with more than one possible outcome. And then the multinomial is like the binomial, but with more than one possible outcome. So it adds up. If you repeat a categorical distribution a bunch of times, it's the number of times you get each result. So these are vector valued. Okay. Then there's also various other ones that may or may not come up but are important. There's the Poisson, hypergeometric, geometric, negative binomial distributions. People who have taken a regular probability or stats class have probably seen all of these. Okay. For a continuous, the most important distribution is the normal distribution. And then also there's the uniform distribution comes up. So those are the two most important ones. Various other ones also come up, beta, chi-squared, exponential, gamma, Laplace. We'll be using beta later today. Laplace will come up in this class for sure. The other ones, maybe, maybe not. Okay, so if you have a random variable x, then x squared is also a random variable. And in general, for any function of a random variable, we can get any function, any deterministic function of a random variable gives you another random variable. And you can get the distribution of this new transformed random variable by saying, well, the probability law for this new transformed distribution, the probability of it being in any set, is equal to the probability of the original random variable x, the being any value such that its transformed value is in this set A. And so that's the probability of x being in the inverse of this transformation. And by inverse here, I mean a set inverse. So for example, x squared, there's not a unique value for, if you say the square is 9, then the original number could have been 3 or negative 3. So this has to be a set valued inverse. If it is a unique inverse, then there's various things you can do to directly transform the CDFs that are nice, but you can figure those out or look those up on your own time. They're not that important. Okay, what is very important is the expectation. So the expectation is the mean of a random variable. If you drew from it unlimited numbers of times, infinite times, then you'd eventually get that the mean of all of those draws comes out to be some number, and that number is called the expectation. So here's an example for drawing from a standard normal up to 1,000,000 times on a log scale. So it started off that I thought the mean was 1.2 because I happened to get a big number right away. But over time, it eventually goes to 0, which is the true mean of the distribution. And that limit all the way to the right is the expectation. So we can talk about that more directly by integrating. So we can, in general, you can take the expectation of any function of a random variable with respect to a random variable x. And the way you do that is you just integrate what you're taking the expectation of, that function of the variable, with respect to the random variable. And so this notation, dp, instead of saying just dx, like a normal high school calculus integral, is, you may have seen something called the Riemann-Stieltjes integral. That's what this is. But so basically, if you have a discrete distribution, that's the same thing as summing and weighting by the probability mass at each point. And if you have a continuous distribution, that's the same thing as integrating, weighting by the probability density dx. Yep. This one? Sure. So if you have like x and y are random variables, then x plus y is itself a random variable. So in that case, it would be the same thing, except that so if we want to do x plus y, so the probability that x plus y is, let's do it with a CDF, some value. Well, that's equal to the probability of the event that x plus y is equal to some value. And so you talk about that as the inverse xy in plus inverse of z. So if you want to actually calculate this value, what you have to do is say, you have to marginalize actually. So you can say the probability that x plus y is less than or equal to z is equal to the probability, so for all possible values of x, it's the probability that, or the probability density, lowercase p, maybe, that x is that particular value of x, and then y is z minus x. So that's, so this is x takes on some particular value, and then y is any of the possible values such that x plus y is less than or equal to z. And so you can do this out for a particular distribution and do that integral. Does that make sense?
So if I want to derive the PDF of that, do I have to take it over to CDF?
Well, you can do it directly with CDFs too. Well, actually, no, in this case, yeah, you'd have to use the PDF for one of them. I think. There might be a direct way to do it, but I'm not sure. Well, so actually, another way to think about it is, say this is the x-axis, this is y-axis, as always. So x plus y less than or equal to z is the same thing as being in this half of the space, right? So sometimes you can do a direct argument where you can say the integral, like the area of this part of the space, because that's just the probability of this being the plus inverse thing. Sorry, this is only true if the numbers are non-negative. Okay? Cool. Okay, so another property of the expectation is that it's linear. So if you know the expectation of x, then the expectation of some constant times x is just the constant times that. And if you know the expectation of two separate things, the expectation of a sum is equal to the sum of the expectations. So that's kind of proven here briefly. The expectation of alpha times g of x plus h of x, that's alpha times the expectation of g plus the expectation of x. So the expectation is a linear function. And that's very useful in general. Okay, another important property is the variance, which is a measure of how spread the distribution is. The definition is this expectation of the squared distance from the mean. So, for example, here's a couple different normal distributions with different variances. So this one is very low variance because it's very tightly packed around its mean. This one's higher variance, highest variance, because it's very spread from the mean. Okay, and then the standard deviation is the square root of the variance. The nice thing about the standard deviation is it's in the same units as the random variable itself. And there's this nice little identity that you can write it this way, you can write the variance that way, but if you just expand it out and use the linearity of the expectation, you get that the variance is equal to this expectation of x squared, which is called the second moment, minus the square of the mean, the first moment. Okay, so when I define the expectation, I actually defined the expectation originally as this long run average, but the technical definition is that integral, the integral of g of x dx, dp of x. But that's okay, because the law of large numbers tells us that actually those two things are equal with probability 1. So if you take any IID sequence of x's and take their sample mean and do it infinitely long, then almost always you will get the expectation. The reason that we're just saying the probability is equal to 1 and not just the thing inside, that the limit of this is equal, is because, so for example, if you're flipping a coin, it's possible that you'll just get heads every time forever. That's incredibly unlikely, but it is an element of the sample space that has a valid probability. So we can't just say this is equal. But for almost the entire sample space, the two things are equal. And this is true for any random variable that has an expectation. But if you've proved it before in a class, you might have assumed that the variance was finite. That's because the proof is harder if you can't assume the variance is finite. But actually, if you do have finite variance, then there's the central limit theorem, which says, kind of speaking loosely here, that if you take the mean of a bunch of IID variables, then in the limit, they look like the mean looks like a normal distribution around the expectation of those variables with their variance divided by n. Okay, another important property is covariance, where you have more than one random variable that are jointly distributed. And you define the covariance as this expectation, the spread of one times the spread of the other. And that's a measure of how x and y are related linearly. And we can do the same kind of thing as we did for variance to write this as the expectation of the product minus the product of the expectations. Okay, and then correlation is covariance divided by the variances of each, or the standard deviations of each. So, as I mentioned, this is a measure of the linear relationship. And if they have a nonlinear relationship, then it's not very meaningful to talk about their correlation. So here's 4 different data sets that have exactly the same correlation value, but look completely different. So here's a typical linear relationship. Here's a linear relationship that actually has a different slope, but we had one outlier, one weird point that messed it all up. Here's one that actually, there's just one outlier in the x. Actually, they have a vertical relationship. For real, there's just one point that was weird, and it screwed up the correlation. And then here's a nonlinear relationship where the linear approximation is not very good and not that meaningful. So be wary of dealing only with correlations or covariances. And these have the same correlation, but if you just scaled them, they would have the same covariance. Okay, and if we have a random vector, then the covariance matrix of that random vector is this matrix of all the covariances between the different elements, which we can also write as basically the same equation as before, just with vectors instead of scalars. And there's an equivalent other expectation of the product versus product of the expectations. Okay, so this covariance matrix, yep.
So in the previous slide, we had nonlinear correlations, right? What are the tools we have to detect those?
So it's a hard question.
I want to answer the
Right, yeah. So it depends on the data. So this is partly the importance of, when you can, actually look at plots of your data and see what's going on. Don't just use these simple summaries.
But in n-dimensional space, that's not
It's not possible to look at all, like an n-dimensional plot, but you can look at various subplots of things and see what they look like. So these are an example where if you can measure the independence, then, for example, these two variables seem to be independent. All of the others don't. So independence is part of this question. Oh, and I didn't mention, but if variables are independent, that means they have zero correlation and zero covariance. But variables with zero covariance aren't necessarily independent. So for example, if you took this, well, I'll just draw it. So these variables are clearly not independent, because if you know the value of one of them, you know there's only two possible values for the other one, but they have zero correlation. So there are lots of non-parametric independence tests and various things. They're hard to deal with. We might talk about them somewhat later in the class. Okay, so if we have this covariance matrix that we define as the pairwise covariances, the matrix of pairwise covariances, so some properties of this matrix is that it's always symmetric, because the covariance is clearly symmetric between the two things. It's also always positive semi-definite, which we can see from this form of it. It's the outer product of a matrix with itself, or the difference of two outer products of matrices with themselves. So that means it has to be PSD, which is an important property in practice. Also, if you multiply a random vector by a matrix and add something, the covariance scales by that matrix on the outside, and the shifting doesn't change anything. Covariance is symmetric, or the covariance matrix is symmetric, except you have to transpose it. And the covariance between the covariance is linear in the first argument, like that. Okay, so, sorry, what?
So what is covariance of X?
Oh yeah, sorry. So this is, I kind of was, put this on the wrong slide. So when I say covariance there, I mean this kind of covariance, the scalar, for the two argument ones.
But what is the single argument?
So that's, you have a vector. You have a vector with n elements. So you define the covariance matrix for that random vector as the covariance between all the elements of that vector. Okay, so that's it for basic probability stuff. Now we're moving on to statistics. So if you have a bunch of data that you got, however you get data, and you want to be able to model that data in some way. You want to be able to answer questions about the data. So one frequent thing that people do, and especially that people did, back in the day with classical statistics, was you say, okay, I have reason to think that this data will be normally distributed, maybe because of the central limit theorem. Then you need to figure out which normal distribution, because normal distribution isn't actually a probability distribution. It's a family of probability distributions with two parameters, the mean and the variance. And so to actually make inferences about your data, or about the process that generated your data, you need to know what the value of that mean and that variance is. So the most common way to figure out which normal distribution fits your data is to say, okay, I want to maximize the likelihood. So the likelihood is the probability density of the data under your model. So it's this P of x given theta. And you want to maximize that over theta, where I'm using theta here to mean the parameters of the distribution. So for a normal distribution, that would be the mean and the variance. And if we have IID samples from the distribution, we maximize the product of the likelihood of each data element under that model. Okay, so as an example, let's say we have a bunch of samples from a normal distribution. So I actually generated these just from a standard normal distribution, and I plotted them with a little jitter so you can actually tell how dense they are. So here's a bunch of different normal distributions with mean 0 but different values of the variance. So the true one that generated the data is this one. That's 0 mean, variance 1. The red one is another one with a wider variance, and the blue one is one with a very tight variance. So if we look at what this value will be for the different, for the data points, we're going to be multiplying the value of this curve at each data point over all the data points. So if we look at this blue curve that's kind of tight, in here, it looks great. You'll get a very high value for all of these data points in the middle. But there are a bunch of data points out here where the density is basically 0. So we're multiplying a bunch of big numbers by a bunch of almost zeros, and we won't get a very good likelihood out. For the red one, nothing is almost 0, but also nothing is that big. So we're multiplying a bunch of not that big numbers. For the black one, which is the true one, in the middle, for most of the data points, we have a pretty high number. And then for all the other data points, the number isn't that low. So that's kind of an intuitive example of why maximizing the likelihood makes sense. So in this case, out of these three models, the black model, the true generating model, has a much higher likelihood than any of the other models. Of course, in this case, if we took a variance that was just slightly higher, the likelihood would be about as good. And in practice, it might actually be a little bit higher than the true model. So we don't necessarily get out the correct model. But that doesn't really matter, because in the real world, there is no correct model. None of the models actually describe how your data was generated. Does that make sense to everyone? Okay. So the problem, or a problem, with maximum likelihood estimation is overfitting. So for example, if we took, actually I think this is a good example. So this correlation, I drew the best fit line, which is the same thing as the correlation in this case. But so you can think of this now as a problem where we're taking this data set and we're saying it was generated by a linear model by a straight line. And if you choose the maximum likelihood for that straight line, assuming Gaussian noise, which is exactly what regular linear regression is, you'd get this line. But that kind of overfit to this outlier in that this particular, clearly the better line is going like this along with the actual line of the data. So we'd prefer to not have to do that. Also, so that's one problem with the MLE is robustness to occasional outliers. Another problem is, let's say we didn't have very much data. Let's say actually we have a normal distribution where the true value looks like that, but we just only have a couple samples. Let's say we just have a couple samples like there, 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 there. Now the maximum likelihood fit to this is going to be much tighter than the true one. That's a terrible picture, I'm sorry. But so in this case, we're overfitting, which we've talked about in class, and there's various other situations where overfitting comes up. So to avoid overfitting, there's a couple different approaches we can take. One popular Bayesian approach is to add a prior. So we think we think the variance can't be that tight, or we think that the line shouldn't be that steep. This can either be if we actually know something about what the model should look like. So we might have some physical knowledge about, say, the model corresponds to some parameter we actually know. So if we were fitting this straight line because of this, we're trying to measure the speed of light, we have an idea of where the speed of light should be. So we can add, and if that's just one of the parameters in the model, we can add a prior around that parameter that says, oh, we think it should be in this area. Or we can also do, if we don't happen to have any knowledge about what the model should look like, or about what the actual value should look like, we can still add priors that say, oh, this shouldn't be some crazy tight variance. It shouldn't be some really complicated, so in linear regression, sometimes we do a thing where we say, not that many values should matter. So we can add a prior that only a few of the features actually matter. That's called the lasso, which we'll talk about later in class. So we can add priors for various kinds of knowledge or preferences that we have for the model. And that can help reduce overfitting. And the way the math actually works is we take this, so before we were just choosing the theta that gives the best x. What we can do instead is throw in Bayes' rule, reverse the direction, and we get the probability of the data given the model, that's the probability of the model, over the probability of the data. And so one way to measure the probability, or one way to talk about the probability of the data is this integral that I wrote here, which is the likelihood of the data under the model integrated across all possible models. Does that make sense? So we're going to choose the, so this is called the posterior distribution. It's the distribution of our beliefs about the model parameters given that we've seen the data. So that depends on, it's based on both our prior belief about the model and on our, the actual data we observed. So what we do is we write, this is the posterior, but actually if we're just choosing the best model, the model that's the mode of the posterior, you notice that this integral is the same for all different values of theta. So we don't actually have to compute it. We can just only look at what makes the numerator the best, and the denominator is always the same. So the maximum is the same. So this is called the maximum a posteriori, or MAP estimate. So it's the same thing as the maximum likelihood, except you add a prior. Oh, sorry. Does that make sense? Okay. So I actually want to do an example. Do we have time? Actually, let's talk about everything else, then I'll come back to the example. Okay. So another choice, rather than choosing the map estimate, is to choose, so we get out this, okay. So let's do this variance example still. And we have a belief about what the variance could be. Let's say it's kind of approximately normal also. That's terrible normal distribution. Okay, so our belief is that the variance should be kind of close. That doesn't make sense. Let's do it for the mean. Sorry. Okay, so our estimation problem is, we have a bunch of data generated from a normal distribution. And it so happened that we got a point over here. But so our estimate of the mean is going to be like there, when the true value of the mean is there. Let's call it 0. So we can say, because we think for some reason, based on prior knowledge of the problem, that we think the mean should be somewhere near 0, but it could be pretty spread out. So this is our beliefs about the value of the mean beforehand. So this is our prior. Now we observe the data, and we get a new estimate of the mean, which is right there. So that's the likelihood function. So based on that, we then have, so based on our observations, we actually, in this case, we would end up with a normal distribution also, where we could say, oh, any of the, this is the most likely value, this mu right here, mu hat, but any of these mu's would make sense, and I can weight how much that mu makes sense based on the data. So based on the data, a mean over here makes no sense, even though a priori I thought it might have made sense. Whereas a mean, so a mean over here is weighted much higher, and so we basically end up multiplying our prior belief, which is symmetric about 0, because that's what we thought, with the likelihood, which is, in this case, happens to be symmetric around the maximum likelihood estimate. And we end up with some kind of gross thing like that. And it's shifted, sorry. So it kind of looks like that. It's somewhere in between 0, which is where we thought it was before, and mu hat, which is what the maximum likelihood estimate would be. So that's the mode of this posterior distribution. We could also use other things to estimate than the mode. A more reasonable choice that a staunch Bayesian would prefer is the posterior mean. So in this case, the mode and the mean are the same, but you could imagine a posterior distribution that's not, where it's not. And so in that case, choosing the posterior mean happens to be the value that minimizes the expectation of the squared distance from the true value, given the expected across different data sets. If you want to minimize the expected absolute distance from the true value, you use the posterior median. And if you use the posterior mode, which is what the map estimate is, that minimizes what's called the 0-1 risk. That makes you the most likely to choose the absolute correct value, but in a continuous setting, that doesn't really make sense. You're never going to choose the absolute correct value anyway. But in a discrete setting, you might want that. So anyway, in general, it's harder to compute the posterior mean or the posterior median than it is to compute the map estimate, because to get the mean or the median, you usually have to actually understand something about the whole distribution. So if it happens that the math works out and it's an analytic case, you can probably get all of them about equally easily, but it's easier to numerically optimize the map than it is to get the other ones. But you can get it from, for example, from sampling from the posterior. And you can sample from this posterior distribution, even though it's a complicated distribution, using a technique called Markov chain Monte Carlo, which we'll talk about a little later in the semester probably. Okay, so also, we have this posterior distribution. Really, ideally, we wouldn't be, yeah, sorry.
So if we are sampling, we probably can store this non-parametric distribution somewhere. How do we store it? Like we calculated the posterior.
So if you're doing MCMC sampling, you don't actually compute the true value of the posterior. So in a particular case, you might know that the posterior is going to be a normal distribution, and then you just store the parameters. If it's non-parametric and you're sampling, you can actually do the sampling in a way that where you don't explicitly represent the posterior distribution. And we'll talk about MCMC later and how that works.
But how would we store the prior?
Oh, the prior.
From where would
Oh, well, so the sampling, I don't want to talk about MCMC right now because it's more complicated. Yeah. Okay. So we have this posterior distribution, and so the mean is probably the best single point estimate to use. The mode also kind of works. The median also makes sense sometimes. But if you can, the best thing to do is don't use a point estimate at all. Just actually have a whole understanding of what the posterior distribution looks like. And then you can do expectations under that posterior distribution to get answers about the questions you want to ask. So that's nice. It's the real full Bayesian thing to do. If you can do it, it's great. The problem is it's hard to do computationally. So there are various things you can do. We mentioned MCMC sampling. We can get samples from the posterior, and then you can answer questions based on those samples. You can also do various things to approximate the posterior distribution and then find the best approximation. So variational Bayes is the most common of those, and we'll talk about that later in the class. Okay, so far we've only been talking really about parametric models, like the normal Gaussian model. The problem with that is that a lot in the real world, even though there's the central limit theorem, your data is still not really going to be Gaussian. There will be, so for example, if you have multimodal data, like something that looks like that, obviously a Gaussian fit to that is going to be terrible. Also, if you have heavy tails, so in practice, the normal distribution expects that you're almost never going to see something beyond like 5, 6 standard deviations out. It's crazily unlikely that you'd ever see that. But in practice, maybe you will, because it doesn't actually follow the normal distribution. So if you just use the normal distribution, then sometimes you'll get really bad answers. And actually, there's some arguments that some people have argued that the reason the financial crash happened a couple years ago was because people assumed normality and independence when things actually weren't normal and weren't independent. So their risk models said, oh, this will never happen, but it did happen. And that's why everything got so bad around 5 years ago. Okay, so instead of using these parametric models, you can do non-parametric things, which have some nicer properties in that they can fit any distribution, but they have some less nice properties in that it's harder to do things with them if you don't assume what the distribution looks like. So those are things like histograms. We talked about kernel density estimation in class. We also kind of talked about KNN density estimation, K nearest neighbor density estimation when we talked about the nearest neighbor classifier. Okay, so what's the point of all this probability stuff? Well, one example is if you're doing classification, you can think about two-class classification as saying, I have this point, I have two distributions, one's a positive and one's a negative distribution where the data came from. Which one is more likely to have generated my data? And the one that's more likely is what you classify as. So this is the basis for a bunch of the classifiers, I think all the classifiers we've talked about so far except the perceptron, where you use Bayes' rule. The probability of the positive class given the data is you flip it, use Bayes' rules, and then you can take the ratio between the probability that it's positive given that point and the probability that it's negative given the sample point. You divide one by the other, the probability of the sample point cancels out, and you have that. So now that you have that, the question is, how do you approximate this term? So the probability of being positive, probability of being negative, you can estimate that just by the ratio of how many positives and how many negatives you have in your sample. So if you get a data set that's about half and half, then you just say half for each. The hard part is the conditional probabilities given the class. So estimating the density of the class. If you do that with kernel density estimation, we talked about in class, that's the Watson-Nadaraya classifier. If you do that with the K nearest neighbor density estimate, which I mentioned, then you end up with the K nearest neighbor classifier. And if you want to do naive Bayes instead, what you do is you assume that these probability of the data given the class is each feature is conditionally independent given the class is your assumption. So then you end up with just multiplying the probabilities of each feature given the class. And each of these distributions, so the probability of the first feature, say the probability of lottery given that it's spam, the word lottery appearing, you model parametrically. So we talked about that in class using either Gaussian distributions for each of those conditional feature distributions or using Bernoulli distributions. You can also use multinomial distributions if you do word counts instead of whether a word was present. Or you can do any distribution you want if you think it'll make sense for your data. So that's what naive Bayes does. And if you have another way to estimate this probability for your data that you think makes sense because you know something about your data, you can just plug it in there, and then you have a new way to classify that is an easy new classifier if you can estimate this probability density. Okay, so that's all I was going to talk about today. I was going to go through an example, but we don't have a lot of time left. So any questions about anything? Sure.
For problem 1.2, if a transaction proceeds with parallel 1, how do you compute its successful rate for
So you're asking about
third subprobability?
right. So Ahmed actually sent out an email about this right before recitation. So the thing here is we have these probabilities. We have this joint probability table, but we don't know for an individual kind of record the joint probability. So the problem is that this question is asking about, we don't actually know what the value is. We don't have enough information to know, whether it's what the actual value is and compute that. But we do have some constraints on what it can possibly be based on that table, on what the marginals are. So if you write out, based on that table, what the possible values of that success is, of whether it succeeds or fails, based on how many of the transactions fall into each of the categories, then you can see that 70% is not possible. Does that help at all? So if you have, so we don't know the actual value of joint on kind of transaction algorithm success, but we do know marginals on, we do know it marginalized out over kind of transaction. So that adds constraints on what the thing can possibly be by adding them up. So if you think about how many transactions, out of all the pool of transactions, how many of them could succeed and how many of them could fail there, then you can see that the 70% proposed number is not possible. Are there any, I think if you have more questions about it, just come to office hours. Anything else? Okay, well, there's a class here in 5 minutes, so we should leave.